Yeah, so this talk is about Project Hamilton, which was a joint research effort between the Federal Reserve Bank of Boston and the MIT Digital Currency Initiative. We looked into building a central bank digital currency transaction processor, which I'll explain more about in this talk. And the views in this talk are my own personal views and not those of the Federal Reserve System. So many central banks around the world are considering launching a central bank digital currency. But what is a CBDC? Ultimately, it's a digital liability of the central bank that would be available to the general public for payments. A CBDC differs from credit cards or payment apps like PayPal because it's a liability of the central bank instead of a claim against a private institution's balance sheet. The cash in your wallet is also a direct liability of the central bank, but it's not digital. So why might you want one? Central banks cite a number of reasons, particularly improved payment system efficiency, financial inclusion, potentially the potential for privacy-preserving digital payments. And in fact, according to the Atlantic Council's CBDC tracker, at least 114 different countries, which represent more than 95% of global GDP, are currently exploring CBDC. So for the purpose of Hamilton and our research, what do we mean when we're talking about a CBDC? So it's important to note that though this is a digital currency, we're not operating in a decentralized setting, like with cryptocurrencies or so-called stablecoins, which run on decentralized blockchain networks. This is a currency that is issued, governed, and run by a centralized entity. So the payment processor is run under a single administrative domain, in this case, the central bank. Users, in this case Alice, have digital wallets with cryptographic keys to authorize transactions moving their money. Other users might choose to use financial intermediaries, like payment service providers, who could interact with the transaction processor on their behalf, for example, by custodying their keys or providing other services. So why is this interesting for us as computer scientists? CBDC transaction processing has a number of unique goals. The first is good performance. And there are two aspects to this. If we want to support a large economy, for example, the United States, we would need to design a system that can potentially support billions of users and a large number of transactions. The second is low latency. If we want this to be an instant payment system similar to a payment app or cash, we need to be able to have really low transaction latency. The next important goal is strong consistency. We really need to prevent double spends. It can't be possible for a user to spend money they don't have, and transactions also need to be completely final once settled, so people have confidence that their payment has been received. Next, it has to be really highly available and resilient. This system would likely be critical national infrastructure, and unavailability of people's funds would be unacceptable. But then also, central banks don't really want to store sensitive user data, so i.e. no user identities, transaction values, payers, payees, balances, things of that nature. So we really want to minimize the amount of sensitive payment data we have to retain at the central bank. And then finally, it would be really nice if we could support innovative features in the future like programmable money. But we already have payment systems today, right? So how do they work and how could our system be different? So most payment systems today in traditional finance use this user account-based model where you basically have a mapping between some customer and an amount of money they have, and then to effect a transaction, it's an increment-decrement algorithm locking two rows in the database to achieve that. This model, although widely used, has two problems. One is sort of like a fundamental lack of privacy. It's pretty clear that there's a mapping between a customer and an amount of money that they have. And when transactions occur, it's clear who the parties are. The next is account contention. If you have a very busy account, like an account that's doing payroll or tax payments, you're going to have to serialize transactions to that account. And this is solved today through batching, but that comes at the cost of much higher latency. And then on the other hand, in the cryptocurrency world, we have this other model called the unspent transaction output-based model, or UTXO model. And I'm going to discuss later and go into a little bit more detail about how that works, but at a high level, you can think of it much more like discrete units of money. And these units of money are encumbered usually by public keys. So this model has a lot of desirable features. The first is that there's no inherent stable identifiers in this model. There's nothing stopping Alice or Bob from using a new public key for every transaction that they make. The second is that there's really no account contention. If I want to pay millions of payments to a single public key, that does not affect any of the other transactions that are utilizing that public key. So let's take a little refresher about how transactions are processed in the UTXO model. Here I'm displaying the tip of the blockchain, and a transaction itself consists of 3 parts. First, it references some inputs previously stored in the blockchain. Second, it describes its outputs, their values, and the conditions under which they can be spent. And third, the transaction contains a signature authorizing the spending of the inputs. So to apply a transaction, we need to perform 3 steps. First, we have to look up the input transaction values and public keys in the blockchain. So there it is, we found it at block 1000. Second, we need to use that data so that we can check the signatures and make sure that the balance of the transaction is less than the sum of the inputs. Finally, assuming that we've been able to successfully validate the transaction, we need to atomically check that the inputs are unspent, mark the inputs as spent, and then append the transaction with the outputs as unspent to the blockchain. So this flow is pretty straightforward, but presents a number of challenges, as I'll show next. So the first is a scalability bottleneck. As you saw in the previous slide, processing transactions actually requires at least 2 round trips to the data source. First, I need to look up the values and public keys for the inputs, and then once I've done the validation, I need to go back to the database in order to effect the transaction. Second, especially in the Bitcoin context, there's a lot of wasteful consensus. Even though in theory, this model of UTXO should be quite scalable, it's limited by the consensus and replicated state machine that it tends to go through. The second is a privacy concern. The blockchain stores public keys and balances and even the entire transaction graph. Now, we're running this in the centralized setting, but even if you kept the blockchain private, the central bank would be the one retaining all of this information. Hamilton solves these challenges. First of all, we achieve high performance. Part of the way we do this is that our transactions require only 1 round trip to process, which I'll explain how later. And our backend that we use to implement this scales linearly to at least 1.7 million transactions per second. We also have much stronger privacy because our system only retains opaque 32-byte hashes to represent unspent funds. And the key idea we use to deliver this is a concept called a distributed scalable UTXO hash set, or UHS, and a co-designed backend to implement this algorithm. So what is our UTXO hash set, or UHS? So recall that to validate a transaction in the UTXO model, we need to look up its inputs from the blockchain. In contrast, in Hamilton, we put a little bit more responsibility on the user, and we modify the transaction format to require them to include the input values and public keys in the transaction itself. So that way, the signature checking and balance of a Hamilton transaction can be completed without doing any lookups. Second, instead of using a blockchain to record outstanding funds, we use a transactional database to maintain hashes of outstanding funds. That is, each unspent input is present as a hash in the UHS database. And processing of a transaction involves deleting hashes for its inputs and inserting new hashes for its outputs. So let's make this concrete and look at how transactions are processed in our system using the UHS. So we have a user, Alice, and she has some wallet software which is tasked with maintaining the UHS hash preimages, i.e. all the public keys and values of outstanding funds that Alice can spend. To create a transaction, Alice first selects input coins and output destinations for them, forming a transaction. She then signs the transaction using her secret key, and finally, Alice sends her transaction to the Hamilton core for processing. Processing a transaction involves multiple steps. First, Hamilton has dedicated components that we call sentinels that check that the transaction is properly signed and preserves balance. Sentinels do not require any access to additional state to achieve this. Sentinels then create something we call a compact transaction, which is an instruction to swap hashes that is devoid of any personally identifiable information. It then sends the compact transaction to the UHS database for processing. The transactional database will then atomically check all the input hashes for the transaction exist in the UHS. If they do, delete the input hashes from the UHS, and finally insert the output hashes in the UHS. Now, we're relying on the user to present the correct values and public keys. Why is it safe for the user to present this information? Our key insight is that in the UHS model, UTXO correctness can be reduced to existence of UHS hashes. That is, after the Sentinel has performed authorization and balance checks, the only check remaining is to see if input hashes exist in the database. This is secure because we use collision-resistant hashing. A user can't reveal a different preimage to a hash commitment in the UHS database because that would violate cryptographic collision resistance, and an incorrect UTXO hash wouldn't exist in the UHS. So to summarize, the UHS abstraction consists of 3 algorithms: validate and compact, which are run by the Sentinels, and these are stateless operations for validation, and then swap, which is our stateful operation in the backend, which actually executes a transaction. This algorithm allows us to decouple transaction local validation from execution. It minimizes central bank data retention by requiring end users to retain some state. And now we can scale validation and compaction, which are stateless operations, independently from execution, which is a stateful operation. And this creates an opportunity to co-design the backend commit protocol to execute swap efficiently. So now I'll talk about how we did that. So our UHS is partitioned across multiple shards for scalability of both the database size and throughput. For our implementation, we use the 2-phase commit protocol in combination with conservative 2-phase locking. Coordinators and shards are replicated using Raft for fault tolerance and high availability. So how do we execute a transaction? Coordinators are constantly gathering compact transactions from Sentinels that have been validated into batches. Batches can vary in size based on demand so that payments do not have to wait for execution. And then there are multiple coordinators, and each executes multiple batches in parallel for scalability. So to actually effect a transaction, the coordinator performs the 2-phase commit algorithm. In this case, for prepare, the coordinator sends a payments batch to the shards and requests that they lock the input UHS hashes for each payment. And the shards respond with a lock status indicating which input UHS hashes could be locked as part of the batch. The coordinator gathers these responses and decides which transactions can complete in the batch and which have to abort. So a transaction that had one or more of its UHS hashes unable to be locked will have to be aborted, and the rest can complete. Once this decision's been made, the coordinator informs each shard about which payments in the batch can complete, and the shards either roll back failed payments by unlocking any input UHS hashes, or finish the swap execution by deleting the input UHS hashes and adding the output UHS hashes. So that's enough about our design and implementation. For our evaluation, previous systems either used like a strongly consistent distributed database, which really can't benefit from the co-design of the system and application, or they use some kind of distributed ledger-based design, which tends to be limited by the throughput of the replicated state machine or the consensus algorithm that's being used. By contrast, our evaluation shows good performance by co-designing the transaction format and the commit protocol. So for our evaluation setup, for the purpose of this talk, we distributed our system across 3 US AWS regions, and we used all balanced 2 input, 2 output transactions, and a database with 1 billion UHS hashes. We also performed an end-to-end test. So our wallet generates and signs a transaction, sends it to a Sentinel, waits for transaction confirmation, and then queries for transaction status a second time to simulate a recipient checking for confirmation. So this slide shows Hamilton's throughput in our 2-phase commit algorithm. It shows that Hamilton's performance scales linearly when increasing the number of logical shards using our workload. We were able to scale Hamilton out to at least 1.7 million transactions per second, and we believe it would continue to scale with additional resources. We also compared against CockroachDB and Postgres, both of which are commercial databases that have significantly slower performance than Hamilton, but this is likely due to the many additional features they have as commercial databases that we don't have or need. We also compared against the Atomizer, which was a blockchain-like structure that we built using the UHS abstraction that you can read more about in the paper. But that system was ultimately bottlenecked by the replicated state machine that provided the ordering service. We also compared against Rollis, which is a very high performance in-memory database. We found that while Rollis could achieve more throughput than our system and scale to accommodate more load with additional threads, Rollis doesn't store any data to disk, which prevents recovery. And secondly, all data must fit in the machine's memory. So for our Rollus benchmark, we ended up having to use a database size that was a fifth of the size than that for a 2PC. This was also a very simplified benchmark. We weren't performing an end-to-end test. We simply performed a simulated swap function. So we think this is a good result because it shows that our 2PC design is at least comparable to the state-of-the-art replicated database. Hamilton also has really good average and tail latency. For end-to-end transactions, this plot is from a 1 million transactions per second benchmark across 3 AWS regions. The tail latency is very low, under 2 seconds, with an average transaction latency of half a second. So in conclusion, we presented Hamilton, a scalable payment processor for CBDC. The code base is open sourced as OpenCBDC, and there's a community of researchers working on that today. There's a lot of interesting future work in progress, particularly on tolerating malicious faults and implementing things like smart contracts. And I'd be happy to take any technical questions you have about the architecture in this talk. Thanks for listening.